Time is the one thing every human being is certain of, and the one thing physicists cannot agree on. You wake up because of time. You age because of time. Every plan you have made, every memory you carry, every fear about what comes next, all of it lives inside time. It is so constant, so immediate, so woven into every moment of being alive that questioning it feels almost absurd. And yet for more than a century, some of the most careful and rigorous thinkers in physics have been building a case that time as you experience it, flowing forward, dividing a real present from a fixed past and an open future, may not correspond to anything fundamental in the universe at all. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. This is not a fringe idea. It is not speculation from the edges of the field. The physicists making this argument are working from the same equations that gave us GPS satellites, nuclear reactors, and the most precisely tested predictions in the history of science. They are reading those equations carefully and reporting what they find. What they find is strange. The laws of physics look essentially the same whether time runs forward or backward. Film a collision between two particles at the quantum level and play it in reverse. The reversed film is physically valid. Nothing in the fundamental equations prefers one direction over the other. The arrow you feel so strongly, the sense that yesterday is behind you and tomorrow is ahead, does not appear to be written into the basic rules of how the universe works. It gets stranger. Write down the equations of physics and look for the special moment called now. You won't find it. There is no variable in any fundamental equation that marks the present as distinct from any other moment. In Einstein's framework, past, present, and future are coordinates in a four-dimensional structure related to each other the way north and south are related in space. The idea that right now is uniquely real, that this moment exists in a way yesterday no longer does and tomorrow does not yet, finds no support in the mathematics. Then there is the deepest problem of all. When physicists try to combine quantum mechanics with general relativity into a single unified theory, time does something even more unsettling. It disappears. The equation John Wheeler and Bryce-DeWitt derived in the 1960s, what should have been the master equation governing the quantum universe, contains no time variable. None. The universe described by that equation does not evolve. It simply exists, static, in a superposition of all its possible arrangements. Time in that picture is not a fundamental feature of reality. It is something that has to be explained, derived, recovered from something deeper that contains no time at all. These are not three separate puzzles. They are three windows into the same problem. And the problem is this: the most immediate, undeniable feature of human experience, the sense that time flows, that now is real, that the future is genuinely open, appears nowhere in the foundational laws that describe the universe with the greatest precision we have ever achieved. Either those laws are missing something important, or our experience is telling us something that isn't true about the underlying structure of reality. Physicists have been arguing about this for over a century. The argument has not quieted down. It has intensified. The people on one side include some of the architects of modern physics, researchers who believe time is an emergent phenomenon, a large-scale approximation that dissolves when you look closely enough at the fundamental level. The people on the other side include equally serious physicists who argue that abandoning time as a fundamental quantity is a mistake that has sent the field down a path it cannot find its way back from. Both sides have genuine technical arguments. Neither side has won. What makes this debate different from most arguments in physics is the nature of the disagreement itself. It is not about the value of a constant, or which competing model fits the data slightly better. It is about whether something you cannot escape, something you are inside of right now, reading these words, is real in any fundamental sense. The disagreement is not about details at the edges of the theory. It is about whether the most obvious feature of your existence is real. To understand what physicists are actually arguing about, you have to be clear about what is being put on trial. The word time carries several distinct meanings at once, and physicists arguing about whether time is real are not always attacking the same one. Some are questioning whether the felt sense of moments passing corresponds to anything in the physical world. Others are questioning whether there is any objective fact about which moment counts as now. Others still are asking whether time is a fundamental ingredient of the universe, or something that emerges from something deeper. These are different questions. Start with the most familiar version. You wake up in the morning and time has passed. The night is gone. What felt like nothing was, from the outside, 8 hours of clocks ticking and planets turning. This felt sense of duration, of moments arriving and receding, is one of the most immediate things about being conscious. Neuroscientists are fairly confident this experience is constructed by the brain. Your perception of the present moment is not an instantaneous snapshot. It is a window roughly a few hundred milliseconds wide, assembled from sensory signals that arrive at different speeds and get stitched together into something coherent. The now you feel is already a kind of reconstruction. That part is not very controversial. The brain builds an experience of flowing time. Nearly Eve, Ryan in the debate accepts this. What is controversial comes next. The question is whether that constructed experience is tracking something real in the physical world, or whether the brain is generating a vivid fiction with no external counterpart. Two physicists can agree that the feeling of time passing is a product of neural processing, and still disagree sharply about whether there is anything in the structure of the universe that actually flows, actually passes, actually moves from past to future. Then there is the directionality problem. Time does not just pass, it passes in one direction. You remember yesterday, you do not remember tomorrow. Eggs break and stay broken. Heat moves from hot objects into cold ones and not the other way. This arrow, pointing always from past to future, feels as fundamental as anything in experience. But the laws of physics, written down in their basic form, do not contain it. Run the equations forward or backward, and the mathematics works either way. The arrow of time you feel in every moment of your life has no obvious home in the equations that are supposed to describe every moment of your life. That gap is one of the central puzzles physicists are trying to close. Separate from the arrow is the question of the present. Even granting that time has a direction, why should any particular moment count as special? Right now feels different from yesterday and tomorrow in a way that goes beyond mere memory or anticipation. There is a sense in which only now is actually happening. This idea has a name in philosophy: presentism. On the presentist view, the present moment is the only thing that genuinely exists. The past is gone, not just inaccessible, but truly no longer real. The future has not arrived, not just uncertain, but genuinely not yet in existence. Reality is this instant and nothing else. The opposing view is called eternalism. On this picture, all moments are equally real. Your birth, this moment, your death, they all exist the way cities in different places all exist, even though you are only standing in one of them. The past has not vanished. The future has not failed to arrive. They are simply located at different coordinates. The words past and future describe relations between events, not differences in their reality. Many physicists lean toward this view because it fits naturally with the mathematics of Einstein's theories, which treat time as one dimension among four and assign no special status to any particular moment along it. There is also a middle position. The growing block theory says the past and present are real, but the future is not yet. Each moment that occurs becomes fixed, joining the permanent structure of what has happened, while what lies ahead remains genuinely open. This preserves the intuition that the future is not yet real, without collapsing into a pure presentism that struggles with what physics tells us. It also has its own serious problems, which surface the moment you press on what the present actually means in a universe where different observers moving at different speeds, disagree about what is happening right now. Each of these positions, presentism, eternalism, the growing block, has been developed carefully, defended rigorously, and attacked from multiple directions. None of them is obviously correct. None of them is obviously wrong. The problems are genuine on all sides, and this is not a situation where more thinking will obviously help, because the difficulties are not just logical, they connect to unresolved questions in fundamental physics about the nature of space-time, the relationship between quantum mechanics and gravity, and what the basic equations of the universe actually imply about the nature of reality. For most of human history, these questions belonged entirely to philosophy. Aristotle wrote about time. Augustine wondered whether time could exist without a mind to perceive it. Kant argued that time was not a feature of the world but a structure that the mind imposed on experience. These are serious contributions, and the questions they raised have never fully been answered, but they were argued in words through intuition and logic, without any mathematical machinery precise enough to generate testable predictions. Before Einstein, whether time was real was mostly a question for philosophers. After him, it became a question you could write equations about. In 1905, Einstein didn't just change physics, he changed the geometry of reality. The idea he introduced was not complicated to state, but it was almost impossible to absorb. Two observers moving at different speeds relative to each other will disagree about whether two events happened at the same time. Not because one of them made a mistake, not because their instruments were faulty, but because simultaneity is not a fixed fact about the universe. It is something that depends on the observer. Two lightning strikes that appear to happen at exactly the same moment to a person standing still on a platform will appear to happen at different moments to a person on a train moving past that platform at high speed. Both observations are correct. Both are measuring what time actually does in their reference frame. There is no higher truth behind them that settles the matter. This is not a perceptual illusion. That distinction matters enormously. We can explain away a lot of things by pointing to the limits of human perception, the imprecision of instruments, the tricks of perspective. Einstein was not pointing to any of those. He was describing a structural fact about the universe. The order of events in some cases genuinely depends on how fast you are moving. At everyday speeds, the difference is too small to detect, but it is there, and at high enough speeds it becomes dramatic. Two events that appear simultaneous to one observer can appear to happen in opposite orders to two observers moving in different directions. Neither observer is wrong. The universe does not resolve the disagreement between them. Hermann Minkowski saw what this implied and pushed it further. In 1908, 3 years after Einstein's paper, Minkowski gave a lecture that opened with one of the most striking sentences in the history of physics. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, he said, and only a kind of union of the two will preserve an independent reality. What Minkowski was pointing to was this: once you accept that different observers measure time and space differently depending on their motion, you have to stop treating space and time as two separate things and start treating them as two aspects of a single four-dimensional structure. What one observer calls distance, another observer moving at high speed calls a mixture of distance and time. What one observer calls time, another calls a mixture of time and distance. Neither description is fundamental. The fundamental object is space-time, the four-dimensional whole. Think about what this means for the concept of now. If you are sitting still and your friend is flying past you on a spacecraft at a significant fraction of the speed of light, your slices of simultaneity, the set of all events you consider to be happening right now, are tilted relative to your friend's slices. Your now and your friend's now cut through the four-dimensional block at different angles. Events that are happening simultaneously for you are not happening simultaneously for your friend. As the spacecraft moves faster, the difference grows larger. This is not a small technical complication. It cuts straight at the idea that there is one universal present moment shared by everyone. The experimental evidence for all of this is overwhelming and direct. Take 2 atomic clocks, the most precise timekeeping instruments ever built. Place one on the ground, put the other on a jet flying around the world. When the jet lands and the clocks are brought together, they no longer agree. The clock that flew has ticked slightly fewer seconds than the clock that stayed on the ground. The difference is small, a matter of nanoseconds, but it is real, reproducible, and exactly what the theory predicts. Time ran at different rates for 2 clocks that started together and ended together, but took different paths through space-time. This is not an abstract theoretical result. GPS satellites orbit Earth at high speeds, roughly 14,000 kilometers per hour. At those speeds, relativistic effects cause onboard clocks to run slightly slower compared to clocks on the ground. But the satellites are also higher up, farther from Earth's gravitational pull, which causes their clocks to run slightly faster. The two effects don't cancel perfectly. Engineers have to correct for both. Without those corrections, the accumulated error would grow at roughly 7 kilometers per day. Every navigation system on Earth, every phone, every aircraft instrument, every shipping vessel, depends on physicists having correctly accounted for the fact that time does not run at the same rate everywhere. This is one of those places where the physics stops being philosophy and starts costing money if you get it wrong. Time dilation is not a thought experiment. It is a calibration problem with a dollar figure attached. What comes out of the Minkowski picture is something stark. The four-dimensional space-time block contains all events, past, present, and future, as coordinates. An event at what you call 5 years ago and an event at what you call 5 years from now are both simply points in the structure. Neither one is more or less there than the other. Minkowski's universe does not have a flowing present. It does not have a preferred now. It has a four-dimensional geometry in which every moment occupies its position the way a point in space occupies its location. The Sun is not more real than the Andromeda Galaxy because the Sun is closer. And by the same logic, in the block picture, yesterday is not more real than tomorrow because it is closer to now. This is where the physics becomes genuinely disorienting, because it appears to contradict something every person takes for granted every second of their lives. The present moment feels absolutely real, the past feels gone, the future feels unwritten, but the mathematics of special relativity offers no support for any of that. It doesn't provide a mechanism for a moving present. It doesn't distinguish between the reality of past events and future events. It simply describes a four-dimensional structure and says that time is one of the axes. Einstein himself was not unaware of what this implied. He lived with it for 50 years. When his closest friend died in 1955, Einstein wrote to the family that the distinction between past, present, and future is, in his words, only a stubbornly persistent illusion. He died himself a month later. He had not softened his position. The universe Minkowski and Einstein described is one where a person sitting at a cafe in Paris in 1921 occupies a location in space-time just as real as a person sitting in a cafe right now. The distance between those two events is measured along the time axis rather than a spatial axis, but the structure that contains them both is equally real at every point. Distance in space does not make a location less real. Time in space-time should not either. If there is no universal now, then the past isn't something that has vanished and the future isn't something that hasn't happened yet. They are simply regions of space-time you haven't visited. The picture that falls naturally out of Einstein's work is one that most people find deeply uncomfortable. The universe, according to this reading, is not a stage on which events unfold over time. It is a four-dimensional object, already complete, in which every event that has ever happened or will ever happen simply exists. Your birth, the extinction of the dinosaurs, your death, all of it present, all of it equally real, spread across the geometry of space-time, the way cities are spread across a map. This is what physicists call the block universe, and it follows almost directly from the mathematics that Einstein handed the world in 1905. The logic runs like this. Special relativity showed that there is no universal present. Two observers moving relative to each other will disagree about which events are simultaneous. Not because one of them is mistaken, because simultaneity itself is not an objective feature of the universe. It depends on how fast you are moving. When Hermann Minkowski reformulated Einstein's work in 1908, he described space and time not as separate things, but as a single four-dimensional structure, space-time. What any individual observer measures as time or space is a kind of shadow, a projection of the underlying four-dimensional geometry onto their particular path through it. The geometry itself is fixed. The geometry itself does not flow. It simply is. This is where the block universe enters. If there is no universal present, no moment that all observers agree is happening right now, then there is no principled basis for calling any moment more real than any other. The present is special to you, in the same way New York is special to someone standing in New York. New York is not more real than London. It is simply where you happen to be. Eternalists say the same thing about time. The moment you are living through right now is not more real than last Tuesday or next March. It is simply where your consciousness happens to be located in the four-dimensional structure. Past and future are directions in space-time, the same way north and south are directions in space. Einstein himself believed this. When his closest friend Michel Bessot died in March of 1955, Einstein wrote a letter to Bessot's family. Michel, he wrote, had preceded him a little by parting from this strange world. This means nothing. For us believing physicists, he wrote, the distinction between past, present, and future is only a stubbornly persistent illusion. Einstein died 1 month after writing those words. He was not speaking loosely. He was not offering comfort and stretching the truth to do it. He meant the statement in the strictest physical sense. Bessot was not gone. He was located at different space-time coordinates. Think about what this actually implies. The dinosaurs are not extinct in the sense of having vanished into nothingness. They exist, fully and completely at their coordinates in the four-dimensional block. The moment you were born exists right now, located 60 or 70 or 80 years behind you in the temporal direction. That moment has not disappeared. It is sitting at its space-time address, unchanged, permanent, as real as anything you are experiencing at this instant. And the moment of your death, whenever it falls, already exists somewhere ahead of you in the block. It has not failed to happen yet. It is simply located at coordinates you have not reached. In the block universe, nothing is ever truly lost. Nothing ever truly arrives. Events simply are at their positions in four-dimensional space-time. The sense that time flows, the deep and immediate feeling that moments are passing, that the present is slipping into the past and the future is becoming now, is, on this view, a feature of how consciousness moves through the block. Not a feature of the block itself. The block does not move. The block does not change. What changes is your position within it, something like the way a reader's eye moves across a page. The page does not change as the eye crosses it. The story was always there in full. The experience of reading it unfolds for the reader, not for the page. This is where most people push back. The future doesn't feel as real as the present. There is something obviously open about tomorrow that yesterday no longer has. Tomorrow feels like it could go different ways. Yesterday is locked. How can they be equally real? Defenders of the block universe have a direct answer to this. The openness of the future is a feature of your epistemic position inside the block, not a feature of the block itself. You remember the past because your brain contains records of it. You do not remember the future because your brain does not yet have access to the information stored there. The asymmetry is in your information, not in the ontology of the universe. The future is closed. You simply haven't read that part of the page yet. Feelings, eternalists point out, are not physics. The sensation that tomorrow is uncertain carries no weight against the mathematical structure of general relativity, which assigns no special status to any moment whatsoever. Some physicists find this answer clean. The equations don't privilege the present. Nothing in the geometry of space-time marks any moment as now. The block universe is what you get when you take the theory seriously and follow it without flinching. Others find it deeply unsatisfying, not because it feels wrong, though it does feel wrong, but because it seems to leave something out. General relativity is not a complete theory of everything. It breaks down at the quantum scale. It cannot currently be merged with quantum mechanics in any fully consistent way, and so the possibility remains that the timeless four-dimensional block is a feature of an incomplete description of the universe. That a more fundamental theory, one that successfully unifies gravity and quantum mechanics, might restore something like a real present, might give time back its teeth. That question is not resolved. It is not close to resolved. Either the equations are right and our sense of a flowing present is the universe's most successful lie, or the equations are incomplete and something important about time has been left out of the model. In 1915, Einstein went further. Special relativity had already done something remarkable. It had dissolved the idea of a universal present moment, showing that simultaneity is a matter of perspective rather than fact. But special relativity was still a theory of flat space-time, a universe without gravity, without mass pulling at the fabric of things. General relativity changed that entirely. Mass and energy, Einstein showed, do not simply sit inside space and time. They warp them. The clearest way to see this is through clocks. A clock sitting on the surface of the Earth where gravity is strong ticks slightly slower than a clock floating in empty space far from any massive object. This is gravitational time dilation, not slower in any loose or metaphorical sense, measurably, precisely, quantifiably slower. The GPS satellites orbiting Earth sit in weaker gravity than the receivers in your pocket, and as a result their onboard clocks run faster by roughly 45 microseconds per day. That is not a large number, but it compounds. Without corrections built into the system, GPS position errors would accumulate at a rate of several kilometers per day. Every navigation system that works on this planet works partly because engineers accounted for general relativity. Time run, s at different rates depending on where you are in a gravitational field. That is not a theoretical curiosity. It is an engineering requirement. Go higher up a mountain and a clock ticks fractionally faster than one at sea level. The difference is tiny, but it is real, and modern atomic clocks are sensitive enough to detect it over a vertical distance of just a few centimeters. Raise a clock by 30 centimeters and it ticks at a measurably different rate than a clock sitting on the floor beneath it. Time is not uniform. It is not steady. It bends. Near a black hole, this bending becomes extreme in a way that strains ordinary language. A black hole is a region of space-time where gravity is so intense that the curvature becomes, at the event horizon, essentially infinite from the perspective of the outside universe. For an observer watching from far away, a clock falling toward a black hole appears to slow as it approaches the horizon. At the horizon itself, from the outside observer's perspective, time appears to stop. The infalling clock does not appear to cross the boundary. It appears to freeze there, suspended, dimming and redshifting, as light struggles to climb out of the gravitational well. The person falling in experiences something completely different. From their own perspective, time flows normally. They cross the event horizon without any dramatic sensation at that specific moment. They continue inward. To them, the universe outside appears distorted and compressed, but they are not frozen, they are moving. So which is true? Is the person inside or frozen at the edge? This is not a question with a clean answer. Both descriptions are physically valid within their respective frames. There is no third perspective, no privileged outside view from which you can say definitively what is happening. The situation is not paradoxical in the sense of being self-contradictory, but it is deeply strange. Time near a black hole is not one thing, it is different things to different observers. and general relativity offers no mechanism for choosing between them. This brings up the deeper implication of general relativity, the one that goes beyond GPS corrections and black hole horizons. In special relativity, space-time was still a kind of fixed stage. The actors moved through it, they experienced time differently depending on their speed, but the stage itself was static. General relativity abolished the stage. Space-time in Einstein's 1915 theory is not a container for the universe. It is the universe. It is a dynamical entity that curves and bends and ripples in response to every piece of matter and energy moving through it. When two black holes collide hundreds of millions of light years away, the distortion propagates outward as gravitational waves, ripples in the fabric of space-time itself, detected on Earth as distortions smaller than a proton. The fabric is real and it moves. Time, in this picture, is not running through the universe. Time is part of the fabric. It is one of the 4 dimensions of the space-time manifold, woven together with the 3 spatial dimensions in a structure that responds to mass and energy. You do not have a universe sitting inside a temporal flow. You have a 4-dimensional object, complete, and what we experience as the passage of time is something that happens inside that object, not something the object moves through. This is the picture general relativity gives, and it creates a collision that has not been resolved. Quantum mechanics was built on different foundations. The Schrödinger equation, which governs how quantum systems evolve, treats time as a fixed external parameter, a background clock that ticks uniformly and provides the independent variable against which everything else is measured. Time in quantum mechanics is not something the theory explains. It is something the theory assumes, built into the scaffolding from the beginning. General relativity says there is no such fixed background clock. Time is part of the dynamical system, not an external setting for it. When physicists try to combine these two frameworks, as they must, because both are needed to describe reality at its most extreme, the conflict between their treatments of time is not a technical obstacle that can be papered over. It is a foundational incompatibility. One theory requires a fixed temporal backdrop, the other says that backdrop does not exist. Both theories are extraordinarily well confirmed within their respective domains. Both cannot be complete as they stand. Quantum mechanics needs a fixed time to do its calculations, and general relativity says no such thing exists. And that collision, unresolved for a century, is where the deepest questions about time actually live. Even setting aside the block universe debate, time has a second problem that is arguably even stranger. The block universe argument is about whether all moments are equally real. That is one kind of puzzle. This is a different kind. Even if you accept, completely and without reservation, that past and future exist on equal footing inside a 4-dimensional space-time block, you still have to explain something that feels blindingly obvious. Time has a direction. Yesterday is different from tomorrow, in a way that north and south are not different from each other. You remember Tuesday but not next Thursday. A coffee cup shatters on a kitchen floor and the pieces do not fly back up. Smoke pours from a chimney and spreads across the sky and never pulls itself back into a column. A block of ice dropped into a warm glass of water melts, and the water never spontaneously refreezes, collecting its held back into a cube. This directional quality runs through every experience you have ever had. It feels like bedrock. It feels like the most obvious thing in the universe. Here is the problem. The laws of physics do not have a direction. Newton's equations of motion are time-symmetric. Run them forward and they describe a planet orbiting a star. Run them backward and they describe the same planet orbiting the same star, perfectly legally, nothing violated. Maxwell's equations, which govern electricity and magnetism and light, are time-symmetric. The Schrödinger equation, which governs how quantum systems evolve, is time-symmetric. Einstein's field equations in general relativity are time-symmetric. Every fundamental law that physicists have written down to describe how the universe works operates identically whether the variable called time increases or decreases. There is no arrow built into any of them. Forward and backward are, at the level of fundamental law, the same. To feel how strange this is, try a simple thought experiment. Imagine filming two billiard balls rolling toward each other, colliding and bouncing apart. Now play that film backward. What you see is two billiard balls rolling toward each other, colliding and bouncing apart. The reversed film looks completely normal. Nothing flags it as impossible. Every detail of the backward film is consistent with Newton's laws. Now imagine filming a raw egg dropped from a countertop. The egg falls, hits the floor, and the shell cracks apart, the yolk and white spreading across the tile. Play that backward. What you see is so jarring it almost looks like a special effect. Broken shell fragments slide together from across the floor. Yolk and albumin gather themselves up. A perfect egg rises smoothly from the tile and into the air. Every intuition you have screams that this cannot happen. But here is what physics says. There is no law in the equation that forbids it. The reversed film does not violate Newton, Maxwell, Schrödinger, or Einstein. Every microscopic interaction happening in that film, every molecule bouncing off every other molecule, is bounced, jars, bowing at. Every microscopic interaction happening in that film, every molecule bouncing off every other molecule, is individually reversible. The egg reassembling itself is, at the level of fundamental physics, a legal move. And yet it never happens. Not once in the history of the observable universe has anyone watched a broken egg reconstitute itself from fragments. This gap between what the laws permit at the microscopic level and what actually happens at the macroscopic level is the arrow of time paradox. Ludwig Boltzmann was the first to formalize it seriously in the 1870s, and it cost him years of his intellectual life. He understood the problem with piercing clarity and spent enormous effort trying to explain how a world of reversible microscopic interactions could produce the relentlessly one-directional macroscopic world we inhabit. He was mocked by some contemporaries who doubted atoms existed at all. He died without seeing the problem resolved. The problem is still not resolved. The asymmetry runs deeper than eggs and coffee cups. Consider memory. You carry a record of the past in your brain, but you have no analogous record of the future. This feels obvious, but ask why. Your brain is a physical system. Its neurons are made of atoms. Those atoms obey the time-symmetric laws we just described. Why should a collection of time-symmetric parts produce something that so firmly points in one direction? Information flows from past to present in a way it does not flow from future to present, and the laws of physics offer no straightforward account of why. Consider causation. You feel certain that the past caused the present, not the other way around. Causes precede effects, but in the time-symmetric fundamental equations, the relationship between earlier and later states is perfectly mutual. The present state of the universe determines the future state, just as surely as the past state determined the present. There is no fundamental asymmetry between influencing forward and influencing backward. The arrow of causation you experience so viscerally has no obvious home in the underlying physics. At the microscopic level, this is precise and specific. Take any single collision between two particles, an electron bouncing off a proton, two gas molecules rebounding from each other inside a container. Record every detail of the collision and reverse the velocities of every particle involved. The reversed collision is physically valid. Every microscopic interaction in the universe is reversible in this sense. None of them prefer a direction, yet pile enough of these reversible interactions together, trillions upon trillions of molecules bouncing around inside a gas or a liquid or a solid, and something emerges at the larger scale that is not reversible at all. The irreversibility is not there in the parts. It appears when you zoom out to the whole. How? That is the question. The standard answer physicists reach for is entropy. Entropy loosely is a measure of how many ways a system can be arranged while still looking the same from the outside. A gas with all its molecules clustered in one corner of a room has low entropy. A gas with its molecules spread evenly throughout the room has high entropy. There are vastly more ways to have the gas spread evenly than clustered in a corner. So if the molecules are moving around randomly, bouncing off each other and the walls, the system will almost certainly be found in a high entropy state rather than a low entropy one. Not because the laws push it that way, but because high entropy states vastly outnumber low entropy ones. The second law of thermodynamics captures this. Entropy in an isolated system tends to increase over time. Disorder accumulates. Order does not spontaneously reappear, and that direction, from lower entropy to higher entropy, is the direction we call the future. This sounds like a resolution. It sounds like an explanation for why time runs one way and not the other. It is, in many respects, a genuine and important insight. It explains why your coffee goes cold and not hot, why a drop of ink spreads through water and never pulls back together, why the past feels fixed and the future feels open. The entropy answer is not wrong. The standard answer, entropy, solves the surface of the problem and opens a much deeper one underneath. The entropy explanation for time's direction works as long as you don't push on it too hard. The second law of thermodynamics is one of the most reliable statements in all of science. In any isolated system, entropy tends to increase. Entropy is roughly a measure of disorder, of how many ways the parts of a system can be rearranged while still looking the same from the outside. A tidy room has low entropy. A scattered one has high entropy. An ice cube dropped into warm water has lower entropy than the lukewarm mixture it becomes. The direction time runs. Forward is the direction entropy runs. This is why you remember yesterday but not tomorrow. The past is the low entropy direction. The future is the high entropy one. It sounds clean. It sounds complete. Then you ask the next question, and everything gets complicated. If entropy increases over time, then the further back you go, the lower the entropy must have been. Follow that logic all the way back, and you arrive at the Big Bang. The universe at its birth was in a state of astonishingly low entropy, not just a little lower than today. Inconceivably, absurdly, almost impossibly lower. Everything we know about the arrow of time, every egg that has ever broken, every drop of ink that has ever spread through water, every fire that has ever burned down to ash, every single one of those irreversible processes depends entirely on that one starting fact. The universe began in a very special state. Physicists call this the past hypothesis, and it is less an explanation than a placeholder for one. Here is why it matters so much. The laws of physics are time-symmetric. Run any microscopic interaction backward, and the reversed version is equally valid. A molecule bouncing off another molecule looks the same in either direction. The equations don't care which way time points. So the laws themselves cannot be the source of the arrow of time. That leaves the initial conditions, the asymmetry we observe everywhere around us, the irreversibility, the decay, the one-way flow, is not built into the rules. It is built into where things started. The universe isn't asymmetric because its laws demand it. The universe is asymmetric because it began in an extraordinary configuration. Roger Penrose has pushed this further than almost anyone. He calculated the probability of the universe beginning with the low entropy we observe. The number he arrived at is staggering, roughly 1 in 10 to the power of 10 to the power of 123. Writing that number out fully would require more digits than there are atoms in the observable universe. It is not a small probability. It is a probability so remote that calling it small is almost misleading. Penrose did not put this number forward to celebrate the miraculous. He put it forward to emphasize that the past hypothesis is not an explanation. It is a fact in desperate need of one. Saying the universe started with low entropy is like explaining why you won the lottery by noting that someone had to win. True, but not illuminating. Some physicists have tried to make the past hypothesis less mysterious by reaching for cosmological frameworks. Sean Carroll, a theoretical physicist at Johns Hopkins, has worked extensively on this problem. His approach accepts the past hypothesis as a real feature of the universe and asks whether a larger picture of cosmology can make the low-entropy beginning less surprising. One proposal involves eternal inflation and a multiverse, in which our observable universe is one of many, with our particular branch having started in a low-entropy state by chance. Whether this resolves the mystery or just multiplies it is genuinely debated. A multiverse where every possible initial condition is realized somewhere doesn't explain why we find ourselves in a low-entropy branch, it simply asserts that such branches exist. Ludwig Boltzmann, who gave us much of the mathematical foundation of statistical mechanics in the 1870s, was tormented by exactly this problem. He understood that entropy increase was statistical rather than absolute. A system overwhelmingly tends toward higher entropy because there are so many more high-entropy states than low-entropy ones. But he also understood the implication. If entropy increase is statistical, then a sufficiently large or sufficiently old universe should spend almost all its time near maximum entropy, with occasional random fluctuations downward. The low-entropy universe we observe is not what you would predict from pure statistical reasoning applied to an eternal cosmos. Boltzmann spent years trying to resolve this, and never managed to his own satisfaction. The problem outlived him. Lee Smolin takes a different position. He argues that appealing to special initial conditions is a sign that something is fundamentally wrong with how the question is being framed. A truly satisfying theory of physics, in Smolin's view, should explain the arrow of time from the inside, from the laws themselves, rather than importing it through boundary conditions that are simply assumed without justification. If the only way to explain why time runs forward is to posit that the universe happened to start in one particular extraordinary configuration, then physics has not explained the arrow of time at all. It has pushed the explanation outside the theory. This is the edge where the entropy story breaks down. The second law is real. Entropy increases. The arrow of time points in the direction of increasing disorder, and that tells you something genuine about why the past feels different from the future. But underneath it sits a question that the second law cannot answer on its own. Why was the entropy low to begin with? The arrow doesn't come from the law. It comes from the starting point, and nobody has a satisfying account of why the starting point was what it was. A theory that explains time's direction by pointing to special initial conditions hasn't explained anything. It has just pushed the mystery one step further back. Quantum mechanics has its own time problem, and it runs even deeper than anything in relativity. Start with what the theory actually says. In quantum mechanics, the fundamental object describing any physical system is something called the wave function. It is not a list of where things are. It is a list of all the places things could be, weighted by probability. Before you measure a quantum system, it is genuinely in multiple states at once. This is not a statement about ignorance. It is not the case that the electron is somewhere definite and we simply haven't looked yet. The theory says the electron occupies multiple possibilities simultaneously, and experiments confirm this in ways that leave no comfortable alternative. The double-slit experiment makes this concrete. Fire a single electron at a barrier with two narrow gaps in it. On the other side, a detector screen records where the electron lands. Do this once and the electron hits at a single point. Do it thousands of times, and the pattern that builds up is not what you would get if the electron were going through one slit or the other. It is an interference pattern. The kind of pattern you get when a wave passes through both slits at once and the two halves interfere with each other. A single electron acting like a wave, passing through both gaps simultaneously, interfering with itself. Block one slit and the interference vanishes. The electron behaves like a particle again. Open both slits and the wave behavior returns. The electron somehow knows. Both slits are available. This is strange. It becomes stranger when you ask what happens at the moment of measurement. When you observe a quantum system, when a detector fires, when a measurement is made, The wave function collapses. All the probability spread across multiple possible states concentrates suddenly into one definite outcome. Before measurement, the electron was in a superposition of positions. After measurement, it is here, at this specific point, with certainty. The before and after are separated by the moment of observation. This is where time enters quantum mechanics, in a way that nobody has ever fully explained. The wave function evolves according to the Schrödinger equation between measurements. That equation is deterministic. Given the wave function now, it tells you exactly what the wave function will be at any future time. It is also completely time-symmetric. Run it forward or backward, the physics is the same. There is nothing in the Schrödinger equation that distinguishes past from future, and nothing in it that singles out any special moment. The equation describes smooth, continuous, reversible evolution. That is all it does. The collapse is none of those things. It is abrupt. It is irreversible. It picks out one outcome from many, and it is not described by the Schrödinger equation at all. The two processes, smooth wave function evolution and sudden collapse, are governed by entirely different rules. The theory uses both, but never explains how or why the switch between them happens. This is the measurement problem, and physicists have been sitting with it since the 1920s. The measurement problem is sometimes described as a technical puzzle waiting for a cleaner formulation. It is more serious than that. It is a question about when and why time stops being symmetric. Before measurement, the quantum description of reality is fully time reversible. After measurement, something irreversible has occurred. A definite outcome exists where many possibilities existed before. That transition is a genuine asymmetry in time, injected into a theory whose fundamental equation has no such asymmetry. Where does it come from? The theory doesn't say. The various interpretations of quantum mechanics are largely different ways of handling this. Each one answers the measurement problem differently, and each one carries with it a different account of time. In the Copenhagen interpretation, the collapse is simply a feature of what happens when a quantum system interacts with a classical measuring device. The wave function is not a description of physical reality. It is a tool for calculating probabilities. When a measurement is made, the wave function updates to reflect the new information. Time enters through the measurement process itself. There is a before, an after, and an irreversible event in between. This sounds reasonable until you ask what counts as a measurement, what distinguishes a quantum system from a classical measuring device, and why the boundary between them exists. No satisfying answer has been produced. The many worlds interpretation takes a different path. In this picture, the wave function never collapses. The Schrödinger equation always holds. When a measurement is made, the universe branches. Every possible outcome occurs in separate branches that can no longer interfere with each other. There is no collapse, no irreversibility, no preferred direction of time. All branches exist simultaneously in the larger wave function of the universe. Time is symmetric. What looks like an irreversible measurement from inside one branch is actually a branching of the universal wave function that is, at the deepest level, perfectly reversible. Pilot wave theory, developed by David Bohm in the 1950s, restores a definite particle trajectory at all times, guided by a real wave that evolves according to the Schrödinger equation. The particle always has a definite position. Measurement reveals that position rather than creating it. This removes the mystery of collapse but reintroduces it elsewhere. The wave function still evolves in a high-dimensional configuration space in ways that are difficult to interpret physically. Relational quantum mechanics, developed by Carlo Rovelli in the 1990s, says that quantum states are not absolute descriptions of systems, but descriptions relative to other systems. There is no observer-independent wave function for the universe. Each system has a quantum state relative to each other system it interacts with. Time in this view is relational in the same way. Events happen relative to physical systems, not against a fixed background clock. This resolves some puzzles and creates others. What all of these interpretations share is that none of them fully dissolves the problem. Copenhagen leaves the boundary between quantum and classical unexplained. Many worlds struggles to explain why we experience only one branch, and why probabilities have the values they do. Pilot wave is difficult to reconcile with special relativity. Relational quantum mechanics is consistent but resists many attempts to make it precise. And every single one of them makes a different implicit assumption about what time is. Whether collapse is real, whether time is symmetric at the fundamental level, whether the wave function is a feature of reality or a bookkeeping device. Pick an interpretation and you've made a bet about the nature of time, and every available bet has serious problems. In the 1960s, John Wheeler and Bryce-DeWitt sat down to write the most ambitious equation in physics, the Schrödinger equation for the entire universe. The goal was straightforward, at least in principle. Quantum mechanics had a master equation. The Schrödinger equation described how any quantum system evolved through time. Apply it to everything, all matter, all energy, all of space-time, and you would have the fundamental quantum description of reality itself. Wheeler and DeWitt sat down to do exactly that. What came out? Stopped them cold. The time variable was gone. Not approximately gone. Not hidden in some corner of the equation where it might be recovered later. Gone entirely. The Wheeler-DeWitt equation, which was supposed to be the quantum heartbeat of the universe, had no time parameter at all. The equation described the quantum state of everything and said nothing about how that state changed, because in this equation, it didn't. The universe, according to the math, was static, not evolving, not flowing, simply existing frozen and complete in a superposition of all its possible configurations simultaneously. This was not what anyone expected. It was not a sign that something had gone wrong with the calculation. It was a sign that something had gone wrong with the assumptions that every physicist had been carrying into the room. The result was not an error, it was a consequence. Here is the problem at the root of it. In ordinary quantum mechanics, time is treated as a background parameter. It is not part of the quantum system being described. It is the clock running outside the system, telling the wave function when to evolve. Schrödinger's equation takes time as a given. Time is the stage. The quantum system is what performs on it. This works perfectly well for electrons and atoms and even large molecules, but when you try to write a quantum equation for the entire universe, there is no outside. There is no clock that isn't part of the system. Everything is inside the equation. Time cannot be a background parameter when there is no background. General relativity makes this worse. In Einstein's theory, time is not a fixed stage at all. It is part of the dynamical fabric of space-time, something that curves and warps in response to mass and energy. Time is a variable in general relativity, not a constant. So when you combine general relativity with quantum mechanics and ask how the quantum state of the universe evolves, you are asking a question that the mathematics cannot process cleanly. Time is both inside the system, because general relativity puts it there, and supposed to be outside the system, because quantum mechanics needs an external clock. The two frameworks pull in opposite directions. When Wheeler and DeWitt pushed through the algebra to find a resolution, what resolved was time itself. It cancelled. The equation that remained described a universe with no temporal evolution whatsoever. Physicists call this the problem of time. It is one of the central unsolved puzzles in all of theoretical physics. Not a footnote in the literature, but a foundational crisis sitting underneath decades of work on quantum gravity. What the Wheeler-DeWitt equation implies, if you take it seriously, is stark. Time is not fundamental. The deepest description of the universe available to physics contains no time. Whatever time is, the thing you feel passing right now, the thing that orders your memories, the thing that separates cause from effect. It is not written into the bedrock equations. It must come from somewhere else. It must emerge. The analogy that helps here is temperature. Individual molecules don't have a temperature. Temperature is a property that appears only when you have enormous numbers of molecules interacting, and it describes the average behavior of their motion. Ask what the temperature of a single molecule is and the question doesn't make sense. Ask what the temperature of a gas is, and you get a precise, measurable, physically real answer. Temperature is emergent. It is real at the scale where it makes sense, and absent at the scale where it doesn't. Time, the Wheeler-DeWitt Equation suggests, may work the same way. At the most fundamental level, the quantum gravitational level, there is no time. There are configurations, there are quantum states, there are correlations between parts of the system. But there is no clock ticking through it all, no parameter measuring how things evolve, because nothing evolves. Then, at larger scales, something that looks and behaves like time appears. The flow you experience, the arrow pointing from past to future, the sense that now is distinct from then. These may be properties of large, complex, thermodynamically rich systems, the way temperature is a property of large collections of molecules, real at that scale, absent at the deepest one. This is not a comfortable position. It means that the most immediate and certain feature of your experience, that time is passing, that things are happening, that the present moment is distinct and real, has no counterpart in the fundamental description of the universe. The universe at its core is not happening. It is not unfolding. It simply is, all at once, in a timeless quantum state. Some physicists treat the Wheeler-DeWitt equation as a mathematical curiosity, a symptom of an incomplete theory that will eventually be fixed when better tools arrive. Others treat it as a genuine revelation about the nature of reality, the clearest signal the mathematics has sent about what the universe is actually like. That disagreement is not resolved. It is, if anything, sharper now than when the equation was first written down. What is resolved is this: you cannot combine quantum mechanics with general relativity without confronting the problem of time directly. A generation of physicists, Rovelli, Barbour, Smolin, built their careers on different answers to the question that Wheeler and DeWitt's equation forced into the open. The equation gave no time. The question it left behind was what to do with that fact. The implication is not subtle. If time doesn't appear in the fundamental equation of the universe, then time, in some very real sense, is not fundamental. Carlo Rovelli does not think time is fundamental, and he has spent decades building the mathematical machinery to back that up. He is not working from the fringes. Rovelli is one of the founders of loop quantum gravity, which sits alongside string theory as one of the two most developed attempts to build a quantum theory of gravity. When he says time doesn't exist at the fundamental level, he is not speculating. He is drawing a conclusion from a framework that thousands of physicists take seriously, one that has been tested against the mathematics of general relativity and found to be consistent. That distinction matters. There is a difference between a philosopher suggesting time might be an illusion and a theoretical physicist who helped construct one of the leading candidates for a final theory of physics saying the same thing. Rovelli is the second kind. The starting point is loop quantum gravity's picture of space itself. In ordinary physics, space is a smooth, continuous fabric, the stage on which everything else happens. Loop quantum gravity says that picture breaks down at the smallest conceivable scales. At the Planck length, roughly 10 to the power of negative 35 meters, space is not smooth at all. It is granular. It comes in discrete chunks of area and volume, the way matter comes in atoms. These chunks are described mathematically by structures called spin networks, webs of nodes and links whose combinatorial properties determine the geometry of space. There is no background stage. Space itself emerges from the relationships between the nodes of the network. Remove the network, and there is no space underneath it. Space is the network. This is what physicists mean when they call loop quantum gravity background independent. The theory does not assume a pre-existing space-time and then put physics into it. It builds space-time from something more primitive. Time in this picture is in the same position as space. It does not exist as a background parameter ticking away behind the scenes. What we call time is a description of how events relate to each other, not a container those events sit inside. This is the relational view of time, and Rovelli pushes it harder than almost anyone. There is no universal clock running through the universe. There is no fact about what time it is everywhere simultaneously. Events don't happen at a time the way objects sit at a location. They happen relative to other events, the way spatial positions are only meaningful relative to other objects. Strip away all the physical systems, and there is nothing left called time. This sounds abstract. The thermal time hypothesis is where it becomes concrete. In any large physical system with many interacting components, thermodynamics picks out a preferred direction. Entropy increases in one direction and not the other, and that asymmetry defines what we call the future. Rovelli and Alain Connes proposed that this thermodynamic direction is where the experience of flowing time actually comes from. It is not that the universe has a built-in arrow of time at the fundamental level. It is that any observer embedded inside a thermodynamically complex system will experience a direction of time. Because the correlations between past states and future states are asymmetric, the flow is real in the same sense that temperature is real. A single molecule does not have a temperature. Temperature is a property that emerges when you have many molecules and you average over their behavior. The experience of time flowing forward is a property that emerges when you have a large, thermodynamically complex system and you are part of it. Real, but not fundamental. Rovelli laid this out in full in his book The Order of Time, which became an unexpected bestseller, which says something about how urgently people want to understand this. His argument there is not just technical, it is almost archaeological, peeling back the layers of what we call time to show that none of them are basic. The distinction between past and future comes from entropy. Without a thermodynamic arrow, past and future are the same direction. The sense of the present, the specialness of now, comes from our particular perspective inside the world. We interact with only a small part of the universe at any given moment, and that limited interaction is what creates the impression of a local now, the impression of flow, the sense that time is moving rather than that we are moving through tonal. J-time comes from the way the brain encodes memory and builds a continuous narrative out of discrete neural events. Each of these features has an explanation. Not one of them requires time to be fundamental. What remains when you remove all of them? Rovelli's answer is a network of events and relations. The fundamental description of the universe is not a movie, not a sequence of moments unfolding one after another. It is something closer to a vast web, in which each node is an event and each connection describes a physical relation between events. The web has no preferred direction. It has no global ordering. It does not happen in time because time is one of the things that emerges from it at larger scales, not one of the things that was there to begin with. The Wheeler-DeWitt Equation, which came up before this, gives Rovelli's position strong mathematical support. The fact that time drops out of the fundamental quantum equation for the universe is not, in his reading, an artifact to be fixed. It is a signal. The mathematics is telling you something. When the only candidate for the fundamental quantum description of the universe has no time variable, the reasonable conclusion is that time is not in the foundations. This is not a proof, but it is serious evidence. The objection almost everyone raises is that this seems to contradict something immediate and undeniable. You are experiencing time right now. The clock on the wall is moving. None of this feels like an emergent approximation. Rovelli's response is patient and precise. Emergent phenomena are not fake. Heat is emergent, and it is real enough to burn you. The solidity of a table is emergent from the electromagnetic interactions between atoms, and it is real enough to stop your fist. The experience of time is emergent from the relational structure of events in a thermodynamically asymmetric world, and it is real enough to organize every moment of a human life. The word emergent does not mean illusory. It means that the description at one level of the physics is a large-scale consequence of a different description at a more fundamental level. For Rovelli, time is not less real for being emergent. A rainbow is emergent too, and nobody thinks rainbows aren't real. Julian Barbour arrived at the timelessness of the universe by a completely different road, and he did it mostly alone. Rovelli built his case from quantum gravity, from the collapse of time in loop quantum structures, from the failure of a universal parameter to survive contact with the Planck scale. Barbour's starting point was older and stranger. He went back to classical mechanics, Newton, Hamilton, the equations physicists had been using for 3 centuries, and asked whether time was actually in them in the way everyone assumed. What he found, after years of working largely outside universities, without the institutional scaffolding that most theoretical physicists rely on, was that it wasn't. Time, he argued, is not a container in which the universe sits and changes. It is a name we give to the sequence of configurations we observe. Strip the name away and what remains is change. Not change in time, just change. This distinction sounds small. It is not. Newton believed in absolute time, a river flowing uniformly through the universe, indifferent to matter, indifferent to observers, ticking at the same rate everywhere, whether anything happened or not. Barbour thinks this is wrong in the deepest possible way. If you removed every particle from the universe, every field, every trace of energy, Newton's time would still be passing. Barbour says that is not a feature of reality. It is a philosophical mistake. Time without change is not time. It is a ghost that does no work and leaves no trace. His central concept is what he calls Platonia. The name comes from Plato, and the idea is this. Imagine the space of all possible configurations of the universe, every arrangement of every particle, every possible shape of every field, laid out like an enormous landscape of distinct snapshots. Each snapshot is complete. It contains everything there is to know about the state of the universe at that instant. Now here is what Barbour insists. These snapshots do not sit inside time. They simply exist, all of them. The universe is not a film being projected frame by frame through a projector. It is a stack of frames, each one real, none of them moving anywhere. What we call time is the path we trace through that stack. This requires a moment to absorb. Change is real. Barbour is emphatic about this. 2 configurations that differ from each other are genuinely different. The difference is real. What is not real is the independent dimension that supposedly carries you from one configuration to the next. In Barbour's picture, there is no river. There are only riverbanks at different positions, and what we call time is the relation between them. His technical framework for this is called shape dynamics. The core idea is that the only physically meaningful quantities in the universe are shapes, not absolute positions, not absolute sizes, not durations, but the ratios and angles that describe how things are arranged relative to each other. The distance between 2 particles means nothing by itself. What matters is the ratio of that distance to other distances. You cannot point to a location in absolute space. You can only describe where something is in relation to everything else. The same logic applies to time. There is no absolute moment. There is only this configuration, and what it is like compared to another configuration. Shape dynamics is not purely philosophical. Barbour and collaborators have shown that it reproduces general relativity in certain regimes, that the same physics you get from Einstein's equations falls out of the shape-based framework under specific conditions. The background independence of general relativity, the fact that the laws of physics make no reference to any fixed coordinate system, maps naturally onto shape dynamics in a way that suggests something is right about the underlying idea. What looks like temporal evolution, when translated into this language, becomes a path through the space of shapes. The path is real. The background time through which the path supposedly moves is not. Here is where the picture gets genuinely strange. If all configurations simply exist, if Platonia is the full structure of reality and nothing is moving through it, then why does time feel like it flows? Why do you remember yesterday and not tomorrow? Why does the universe appear to have a direction? Barbour's answer involves memory, and it is one of the most striking ideas in the whole debate. Each configuration of the universe that constitutes a present moment contains records of configurations that came before it. Your brain holds memories. Fossils hold shapes that match living organisms that existed earlier. Photographs carry light patterns from past arrangements of matter. The craters on the moon record impacts. The light reaching a telescope left its source thousands of years ago. Every present configuration is saturated with information about previous configurations, not because time carried those configurations away into the past, but because the present configuration was built from them and retains their imprint. This is why you feel like you've come from somewhere. Not because a river called time has carried you here, because you, right now, in this precise configuration of neurons and memories and physical state, contain traces of what came before. The past is not behind you in some temporal hallway you can no longer enter. The past is inside you, encoded in the structure of the present. The sense of temporal flow on this view is the experience of a configuration that is full of records. The feeling of moving forward through time is the feeling of being a complex system whose current state is deeply shaped by prior states, a system that contains its own history. Whether this is a complete explanation of time's arrow, or an elegant redescription of the same mystery wearing different clothes, is a question Barbour's critics press hard. But the framework is coherent and mathematically serious, and it arrives at timelessness by a route that has nothing to do with quantum mechanics, nothing to do with spin networks or Planck scale discreteness. It comes from asking what Newton actually needed time for, and finding that the answer is less than he thought. The past doesn't recede because time carries it away. The past is visible in the present because the present carries its records. In 1983, two physicists did something almost no one noticed at the time. They derived the flow of time from a completely timeless quantum equation. Don Page and William Wootters were working on one of the strangest consequences of the Wheeler-DeWitt Equation. That equation, as the previous section established, describes the quantum state of the entire universe without any time parameter at all. The universe, according to it, simply sits there, static, frozen, unchanging. Page and Wootters took that conclusion seriously and then asked a different question. Not whether time could be put back into the equation from outside, but whether time could somehow arise from within it. Their proposal was this: take the quantum state of the universe, timeless, static, satisfying the Wheeler-DeWitt equation. Now divide the universe into two parts. One part is a clock system. The other part is everything else. All the matter, all the fields, all the physical processes that make up the rest of reality. These two parts are quantum entangled. And entanglement, in quantum mechanics, means the state of one part is correlated with the state of the other in a way that cannot be reduced to the properties of either part alone. When you look at the clock, you find a specific reading. When the clock reads a certain value, the rest of the universe is in a specific corresponding configuration. Different clock readings correlate with different states of everything else. From outside the system, nothing is changing. The global quantum state is static. There is no evolution, no flow, no before or after. But there is no observer outside the universe. Every observer who actually exists is inside the system, part of the entangled whole. And from the inside, from the perspective of an observer who is part of the rest of the universe looking at the clock, something different appears. The clock has a definite reading. That reading corresponds to a definite state of the surrounding world. As the entanglement structure of the system varies across configurations, the clock reads differently, and the surrounding world looks different. The observer experiences this as change, as time passing. This is not a vague metaphor. Page and Wootters worked through the mathematics carefully, and what they found was remarkable. Starting from a quantum state with no time evolution at all, they were able to derive the time-dependent Schrödinger equation, the standard equation that describes how quantum systems change over time. That equation was not put in by hand. It emerged from the correlations between entangled subsystems of a timeless whole. Time, in their framework, is what entanglement looks like from the inside. For roughly 3 decades, almost nobody cared. The paper was acknowledged, noted occasionally in discussions of quantum gravity, and largely set aside. It seemed too abstract, too remote from anything testable, too philosophically strange to be taken as a serious physical proposal. That changed gradually, as the problem of time in quantum gravity became harder to ignore, and as experimental tools for manipulating small quantum systems became more precise. In 2013, a group of physicists at the Istituto Nazionale di Ricerca Metrologica in Turin ran an experiment that tested a version of the Page-Wootters Mechanism in a small optical system. They prepared pairs of entangled photons, used one photon as a clock and the other as the system being observed, and measured whether the correlations between them were consistent with the mechanism's predictions. They were. The experiment did not prove that time is generated by entanglement at a cosmic scale. It was far too small for that. But it demonstrated that the mathematical structure Page and Wootters described was not merely formal. It produced predictions that could be confirmed in the laboratory. The implications, if the mechanism scales up to the universe as a whole, are significant. Time is not a dimension the universe is embedded in. It is not a background clock ticking away independently of everything else. It is a relationship, a set of correlations between entangled parts of a quantum system. Different subsystems of the universe serve as clocks for other subsystems. The experience of duration, of one moment following another, is the experience of being a physical system correlated with other physical systems in a particular structured way. Take away the entanglement and the correlations disappear. Take away the correlations and time disappears with them. This reframes the question of time's reality in a specific and interesting way. The Wheeler-DeWitt Equation says the universe as a whole has no time. The Page-Wootters Mechanism says that is consistent with time being perfectly real for observers inside the universe. There is no contradiction. The global state is timeless. The relational structure is temporal. Both statements are true simultaneously, because they are statements about different things. The whole versus the parts, the view from outside versus the view from within. There is something almost vertiginous about this. The sensation you have right now of being located in a present moment, of the past being behind you and the future ahead, would be, on this account, a consequence of the fact that you are a quantum system entangled with other quantum systems. The clock on the wall, the decay of atoms in your body, the firing of neurons in your brain, all of these are entangled with each other in ways that produce consistent correlated readings. That web of correlations is time, not a container those processes happen inside, the correlations themselves. Julian Barbour would say something similar. Change is real, but time as an independent backdrop is not. The Page-Wootters picture adds a quantum mechanical mechanism for how that change gets structured, how it becomes ordered, how it comes to feel like a progression, rather than a jumble of disconnected states. The entanglement does the work that time was supposed to do, and it does it without requiring time to exist as a fundamental element of the theory. If time is relational, if it lives in the correlation between entangled quantum systems rather than in a background dimension, then asking whether time is real is like asking whether a conversation is real. It doesn't exist without two participants, but between them, it is entirely genuine. Lee Smolin helped build loop quantum gravity alongside Rovelli, looked at the same equations, and arrived at the exact opposite conclusion. That is worth pausing on. These are not two physicists working in different traditions, talking past each other across a disciplinary divide. Smolin and Rovelli were collaborators. They came up through the same research program, wrestled with the same mathematical objects, and read the same results. And where Rovelli looked at the Wheeler-DeWitt Equation and saw confirmation that time is not fundamental, Smolin looked at the same equation and saw a warning sign that something had gone seriously wrong. His argument is not that the math is incorrect. It is that the math is incomplete, and that the conclusions physicists have drawn from it represent one of the most consequential category errors in the history of the field. The book where Smolin laid this out most forcefully is called Time Reborn, published in 2013. The central claim is stark. If the laws of physics are genuinely timeless, if they exist outside of time, fixed and eternal, governing the universe from some mathematical beyond, then they cannot be explained. You cannot ask why they are what they are. There is no process by which they came to be. No earlier state of affairs selected them. They simply are, without cause, without history, without any account of why these laws rather than some other set entirely. For Smolin, this is not a deep truth about physics. It is a dead end. A timeless law is an unexplained law, and unexplained laws are a signal that you haven't actually understood what you're looking at yet. Flip it around and the argument becomes clearer. If time is real, genuinely, fundamentally real, then the laws of physics have a history. They can change. They can evolve. And if they can evolve, then in principle you can ask why they evolved into the particular form we observe. And in principle you can construct an explanation. The question becomes tractable. The moment you remove time from the picture, you remove the possibility of that explanation entirely. Smolin is direct about where this leaves the block universe picture. He does not think the block universe is obviously wrong as a description of what the equations say. He thinks the equations are incomplete, and that taking them as a final account of reality is the mistake. The time symmetry of current physical laws is a feature of our current incomplete theories. When physicists finally write down a successful theory of quantum gravity, one that actually works rather than producing infinities and contradictions, Smolin predicts that time will come back, not as an approximation, not as an emergent convenience, as something fundamental, built into the structure of the theory at the deepest level. This is not a vague hope. Smolin has spent decades trying to build the technical case for it. His argument connects to a broader proposal about how the laws of physics themselves should be understood. The laws we observe appear to be, in a specific technical sense, finely tuned. The constants of nature sit in a narrow range that permits complex chemistry, stable atoms, long-lived stars, and ultimately the kind of slow, patient complexity that produces life. This has bothered physicists for a long time. The standard response invokes the multiverse. There are many universes with different constants. We happen to live in one, where the constants permit us to exist, and there is nothing more to explain. Smolin finds this unsatisfying. It explains the observation by making the explanation impossible to check. His alternative is cosmological natural selection. The idea runs like this. When a black hole forms, it may give rise to a new universe with slightly different physical constants, a kind of cosmic reproduction. Universes that produce many black holes leave more descendants than universes that produce few. The laws of physics we observe may have been selected over many generations of universes because they happen to produce a large number of black holes. The constants are what they are not by chance, and not by anthropic selection, but because they have been shaped by a process that works like evolution. What matters here is the implication for time. Cosmological natural selection only makes sense in a universe where time is real. Evolution requires succession. It requires that earlier states give rise to later ones, that history has genuine content, that the past actually happened and the future has not yet been determined. A timeless block universe cannot evolve in any meaningful sense. If all moments are equally real and equally fixed, there is no room for a process that selects some configurations over others across generations. The entire framework collapses without a real direction of time running through it. Smolin's critics point out that cosmological natural selection has its own serious problems. The mechanism of reproduction through black holes is speculative. The constants that maximize black hole production do not obviously match the constants we observe, and the theory is difficult to test in any direct way. Smolin acknowledges the objections. He does not present cosmological natural selection as settled science. He presents it as the kind of explanation that becomes possible once you treat time as real, and impossible the moment you treat it as emergent or illusory. The most striking part of Smolin's position is what he does with the subjective experience of time. Every other approach in this debate treats the felt sense of the present moment as something that needs to be explained away, a product of neural processing, an artifact of thermodynamics, a macroscopic approximation that dissolves at the fundamental level. Smolin refuses this move. He argues that the present moment, the raw experience of right now, is not a bug in our cognitive machinery or a confusion to be resolved. It is data. It is the most immediate and universal observation any conscious entity can report. A physical theory that cannot account for it, or that dismisses it as an illusion, is not more rigorous than a theory that takes it seriously. It is less complete. For Smolin, the sense that right now is real is not a brain bug to be debugged. It is the most important datum physics has been ignoring. The physicists working on quantum gravity are not the only ones trying to figure out whether time is real. Philosophers have been running a parallel argument for decades, and the two communities are only beginning to talk to each other. While Smolin and Rovelli debate equations, philosophers have been building arguments from logic, language, and the structure of reality itself. The conclusions they've reached are unsettling in their own right. And what makes this philosophical debate particularly important is that it doesn't depend on any particular interpretation of quantum mechanics. It cuts deeper than that. The question of whether the past still exists, whether the future already exists, and whether only right now is real, turns out to be extraordinarily difficult to answer even without a single equation in sight. Start with the position that most closely matches common sense. Presentism holds that only the present moment is real. The past is genuinely gone, not stored somewhere, not accessible in any physical sense, simply absent from reality. The future is genuinely not yet there. This is the view most people hold without knowing it has a name. When you say that Julius Caesar crossed the Rubicon, the presentist reading is that this sentence describes something that no longer exists. The crossing happened. It influenced the world. But the event itself has vanished completely, leaving only its effects behind. This matches how most people intuitively understand causation, identity, and change. Things happen and then cease. New things come into being. Reality is an ever-moving knife edge between a nay past, and an unformed future. The problem is that special relativity makes presentism almost impossible to maintain. If there is no absolute simultaneity, if two observers moving at different velocities genuinely disagree about which events happen at the same time, then the question of what counts as the present becomes observer-dependent. Consider two events happening far apart, a supernova in one galaxy and a birth in another. One observer might find these simultaneous. A second observer, moving rapidly relative to the first, might find the supernova happened before the birth. A third, moving the other way, might find the birth came first. None of these observers is wrong. None is measuring carelessly. The disagreement is written into the structure of space-time. So if only the present exists, which present is the of? That gets to count as real. If the answer is that each observer has their own real present, then reality is fractured into as many simultaneous presents as there are observers moving at different speeds. That is an uncomfortable place to end up. Eternalism takes the opposite position and avoids the relativity problem entirely by conceding it. All moments in time are equally real. Your birth, this moment, your death. All of them exist with equal status in the four-dimensional block. The words past and future describe relations between events in the block, not differences in their degree of reality. Just as New York and Tokyo are both real, despite being in different places, 1955 and 2025 are both real, despite being at different temporal coordinates. The relativity problem dissolves immediately. There is no single present that needs defending. Every observer carves out their own slice of the block, and all slices are equally valid cuts through an equally real structure. But eternalism creates a different set of problems. If the future is already real, if your death exists right now as a fixed region of space-time, in what sense does anything genuinely happen? Change seems to become an illusion. You don't change. Rather, your earlier temporal stages differ from your later ones, the way the left side of a stick differs from the right side. Nothing becomes different. Everything simply is different at different coordinates. This is a coherent position, but it sits badly with ordinary experience and raises serious questions about causation and agency. If the event of your choosing what to eat tomorrow already exists at a fixed location in the block, what does it mean to say you are about to choose it? Eternalists have answers. They say that causation is real. Later events in the block depend on earlier events in a way that is perfectly objective. Change is real. It just means temporal variation, rather than something coming into being that wasn't there before. Free will is harder. Most eternalists who take free will seriously argue for compatibilism. The choice exists in the block, but it is still genuinely yours because it flows from your own mental states rather than external compulsion. Critics find this unsatisfying. The debate over free will in a block universe has been running for decades with no resolution in sight. The growing block tries to find a middle path between these two positions. On this view, the past and present are real. They exist in the fixed block, but the future does not yet exist at all. Time has a genuine direction because the block is asymmetric. It grows. New moments come into being at the leading edge, become part of the permanent past, and the block extends further. This preserves the reality of change in a strong sense. New events genuinely come into existence rather than being merely revisited coordinates. It also preserves the fixity of the past, which matches the way causation seems to work. What has happened cannot be undone. The difficulty is that the leading edge of the growing block, the present moment, faces the same relativity problem as presentism. Different observers moving at different velocities disagree about which events are simultaneous, which means they disagree about where the leading edge is. If the present is the edge of the block, and that edge is observer-dependent, then the very boundary between real and not yet real becomes a matter of perspective. Some philosophers have argued that this can be handled with careful analysis of what relativity actually claims. Others think it is fatal to the growing block, in the same way it is fatal to presentism. 3 positions, decades of debate, and not one of them undefeated, which tells you something about how hard the underlying question actually is. Because neither presentism nor eternalism fully works, a cottage industry of intermediate positions has grown up around the problem. The debate between those two camps has been running long enough that philosophers have had time to notice where each one breaks down and to start building alternatives. Some of those alternatives are genuinely creative. None of them are clean. The most developed intermediate position is the growing block universe. The philosopher C.D. Broad proposed the core idea in the 1920s, and more recently Michael Tooley has given it a rigorous formal treatment. The picture is this. The universe is a 4-dimensional block, but not a completed one. New moments keep coming into existence and becoming permanently fixed. The past is real and immutable. Everything that has happened is now a permanent structure of the block. But the future has not yet been added. It simply doesn't exist anywhere. The block is growing moment by moment in the direction we call forward. This is attractive because it seems to honor 2 things simultaneously. Change is genuine. New events really do come to be, rather than merely being revealed as the universe shuffles through a finished structure. And the past is fixed. Nothing that has already happened can be undone or altered. The sense that the present moment is special, the leading edge where reality is actively being produced, gets a real physical basis. Then David Chalmers pointed out something strange. If every past moment is equally real, and you are located somewhere in that block, there is no way from the inside to confirm that you are actually at the leading edge. Every moment in the entire block would feel exactly like the present. A person sitting at a moment that was the present 2 hours ago or 2 centuries ago would have an experience indistinguishable from yours. They would feel the urgency of now, remember the past, anticipate the future. From within any moment in the block, the subjective experience is identical. So how do you know you were at the growing edge rather than embedded somewhere in the long-fixed interior? You don't. You cannot. The growing block doesn't just have a technical problem with relativity. It has an epistemic problem that cuts at the very feature it was trying to explain. The specialness of now was supposed to be the point. The theory cannot guarantee that now is actually special. The moving spotlight theory takes a different approach to the same underlying intuition. It accepts the full static block universe, all moments equally real, the whole four-dimensional structure already complete. But it adds one thing, an objective present that travels through the block. Think of a searchlight sweeping across a fixed landscape. The landscape is entirely real everywhere the light isn't shining. But there is a fact about which patch is illuminated right now. That illuminated patch is the present. Past and future moments exist, but the present is the one the spotlight has reached. This preserves the block universe's clean relationship with relativity's mathematics and gives the present a genuine physical distinction. The appeal is obvious. It seems like a neat surgical fix. Keep everything physicists like about the block universe and add back the one feature that ordinary experience demands. The problem is that the spotlight is doing a lot of work and explaining almost nothing. What exactly is it? It isn't a physical object, no particle, no field, no known form of energy. How fast does it move? 1 second per second is the obvious answer, but 1 second per second relative to what? The block universe has no external time for the spotlight to move through. In what medium does it travel? If space-time is the complete structure and the spotlight is moving through space-time, you need a second kind of time to describe that motion, and then a third kind to describe the motion of the spotlight through the second kind, and so on without stopping. The moving spotlight doesn't solve the problem of the present. It names the problem and calls the name a solution. Philosophers are aware of all of this. The positions keep multiplying precisely because each new proposal patches one hole and opens another. There are variants of the growing block that try to sidestep the Chalmers problem by adding observer indexing. There are versions of the moving spotlight that try to build the second-time structure into the formalism explicitly. Each attempt generates a new round of objections, a new literature, new refinements. The gap between what physics describes and what experience demands is deep enough that no framework spanning both sides is held up without serious damage. The fact that this many serious proposals exist, each solving some problems and creating others, is a reliable sign that the right answer hasn't been found yet. The most radical recent proposals don't just question whether time is fundamental, they question whether space-time itself is fundamental. This is a different kind of claim. The arguments from Rovelli and Barbour take the equation seriously and conclude that time drops out of the deep description of the universe. The arguments from Smolin push back and insist time must be restored. But a third line of work, growing out of string theory and black hole physics, asks a stranger question altogether. Not where time went, or how to bring it back, but where space-time came from in the first place. The starting point is black hole thermodynamics. In the early 1970s, Jacob Bekenstein noticed something odd about black holes. The entropy of a black hole, the measure of its hidden disorder, is not proportional to its volume. It is proportional to the area of its event horizon. Stephen Hawking confirmed this and extended it. The amount of information a region of space can contain is set by the area of its boundary surface, not by the three-dimensional space inside it. Think about what that means. If you wanted to encode everything happening inside a sphere, you would not need storage proportional to the volume of that sphere. You would need storage proportional to its surface area. Everything in the interior can be described by information written on the skin of the region. This became known as the holographic principle, and it was deeply strange. The obvious objection is immediate. We live in 3 dimensions. We move through 3 dimensions. We build furniture in 3 dimensions. How could a 3-dimensional reality be completely described by a 2-dimensional surface? That sounds like a trick, but physicists who worked through the mathematics found it was not a trick. It was pointing at something real about how information and geometry relate to each other. The interior is, in a precise technical sense, redundant. The boundary contains everything. Juan Maldacena sharpened this into something exact in 1997. Working within string theory, he found a specific case where the holographic principle becomes a full mathematical equivalence. On one side, a theory of gravity in a particular curved spacetime called anti-de Sitter space. On the other side, a quantum field theory with no gravity at all, living on the boundary of that spacetime. These 2 theories are identical. Every calculation you can do in one corresponds exactly to a calculation in the other. Every particle in the bulk gravitational theory corresponds to some configuration of the boundary quantum field theory. This is the ADSET-CFT correspondence, and it has been one of the most studied results in theoretical physics in the last 3 decades. What it implies for time is striking. The interior spacetime, the full 4-dimensional region where gravity operates, where time is a dimension, is encoded in a quantum system on the boundary. That boundary theory has no gravity. It does have time in the sense of quantum evolution, but the time that appears in the interior spacetime is not the same as the time parameter on the boundary. The geometry of the bulk, including the time dimension of the bulk, is a derived structure. It is not put in by hand. It emerges from the quantum physics of the boundary. If space-time can emerge from a quantum theory that does not itself live in that space-time, then space-time is not fundamental. It is a consequence. Something else is prior, and space-time is what that something else looks like from the inside. Mark van Ramsdonk pushed this further around 2010. He found that the geometric structure of the bulk space-time, the way different regions are connected, is directly tied to entanglement in the boundary quantum theory. Disconnect 2 regions of the boundary by removing their entanglement, and the corresponding regions of the bulk geometry pull apart. The smooth interior space-time tears, restore the entanglement, and the geometry reconnects. The connectivity of space is a function of the entanglement structure of the quantum theory. Brian Swingle developed this further using ideas from quantum information, showing that the geometry emerging from the boundary theory has precisely the structure you would expect if space were built from entanglement. The slogan that physicists started using is short and strange. Space-time from entanglement. Entanglement is the primary ingredient. Space is what happens when quantum systems are correlated with each other in the right way. Time is part of that derived geometric structure. This connects to an idea sometimes called ER equals EPR. Einstein-Rosen bridges are wormholes, tunnels through space-time connecting 2 distant regions. Einstein-Podolsky-Rosen pairs are entangled quantum particles. The claim, developed by Maldacena and Leonard Susskind, is that these 2 things are not merely analogous, they are the same thing described in different languages. Entangle 2 quantum systems and you have created a geometric connection between them. The wormhole and the entanglement are one object. This picture is not proven. It works clearly in the particular mathematical setting of ADS-CFT, which uses a kind of curved space-time that does not precisely match the universe we live in. Extending it to cosmology, to the actual universe with its positive cosmological constant, remains an open technical problem. The program has serious critics who argue that the mathematical equivalence in ADS-CFT does not prove that space-time is emergent in any philosophically meaningful sense, only that the same physics can be described in 2 different ways. But the research program is serious and active. Physicists are building a picture in which quantum information, entanglement, correlations between subsystems, the flow of quantum data, is the foundational layer of reality. Space-time is not the stage on which quantum physics performs. Space-time is a structure that quantum physics assembles, under the right conditions, from something that has no spatial or temporal character of its own. If space-time is woven from entanglement, then time was never a dimension the universe lived in. It was always a consequence of the way quantum information is organized. Whatever the physics says, you experience time, and that experience is so immediate and so constant that it seems absurd to dismiss it. You feel the past as something gone. You feel the future as something unformed. You feel right now as the only moment that is actually here. That sense is not occasional or faint. It is the background condition of every thought you have ever had. And yet the physics described in the preceding sections treats that feeling as somewhere between irrelevant and illusory. So the question becomes urgent. What exactly is the brain doing when it produces an experience this vivid and this universal? The first thing to understand is that the brain is not recording time the way a camera records light. It is building a model. At every moment, your nervous system is taking incoming sensory signals, comparing them to predictions it has already made about the world, and updating its picture accordingly. The present you experience is not a snapshot of reality arriving cleanly at your senses. It is a construction assembled from signals that travel at different speeds, processed by different neural pathways, integrated over a window of several hundred milliseconds. What feels like now is actually a brief interval of time stitched together and presented to awareness as a single moment. The scenes are invisible, but they are there. This matters because it means the brain can get the sequence of events wrong. Under the right conditions, it does exactly that. A stimulus applied to your ankle reaches your brain slightly later than a stimulus applied to your hand because the nerve pathway is longer, yet you experience them as simultaneous. Researchers have designed experiments where two events are reversed in presentation, and subjects report experiencing them in the wrong order. The brain retroactively adjusts its timeline, deciding after the fact which event came first, and the conscious experience reflects that adjustment rather than the physical sequence. You are not perceiving time directly, you are receiving a narrative the brain has already edited. The subjective rate of time is equally unstable. High emotional arousal stretches the felt duration of an event. Fear makes seconds feel like minutes. Boredom has the same effect. Deep absorption in a task compresses time in the other direction and hours vanish. Body temperature shifts alter the perceived speed of an internal clock. Age changes it systematically over decades. None of this is exotic. Everyone has lived it. But taken together, these variations tell you something structural about the nature of temporal experience. The flow of time that feels so objective and so constant is actually a variable output of neural processing sensitive to arousal, attention, chemistry, and context. Then there is the question of the felt specialness of now. Why does this moment feel different from the moment an hour ago, which you now only remember, or the moment an hour from now which you can only anticipate? Neuroscientists describe the brain as fundamentally predictive. It models the immediate future continuously, generates expectations, and compares incoming data against those expectations. The present moment is the place where prediction meets outcome. The sense of nowness may be exactly this, the ongoing collision between the brain's model and the world's response. If that account is right, the special quality of the present is a feature of how the brain operates, not a feature of physics. Here is where the argument splits in exactly the way the larger debate splits. Rovelli and Barbour look at this neuroscience and find it entirely consistent with their position. If the brain produces the experience of temporal flow through its own internal processing, then flow is a biological phenomenon. The universe underneath does not need to flow for the brain to generate that sensation. A static network of relations or a frozen block of space-time can give rise to a brain that experiences time as rushing forward, because the brain is a physical system that processes differences between states and calls that processing now. The experience is real as an experience. It has no counterpart in the fundamental structure of the universe. Smolin looks at the same neuroscience and draws a different conclusion. The brain is a physical system embedded in a physical world. When it tracks change, anticipates the future, and remembers the past, it is responding to something. The question is whether that something is the genuine structure of a time-bound universe or merely the local statistics of a block. Smolin's view is that the brain's sensitivity to time reflects something real about time, the way the eye's sensitivity to light reflects something real about photons. The fact that the brain constructs its experience does not mean the experience is tracking nothing. It may mean the brain has evolved to track a feature of reality that physics has not yet described adequately. What makes this genuinely difficult is that neither interpretation makes a wrong prediction about experience. Both the block universe and a fundamentally flowing universe would produce exactly the kind of brains we have, constructing exactly the kind of temporal experiences we report. The neuroscience doesn't break the tie. It describes what the brain does without settling whether the brain is faithfully representing deep structure or creatively constructing something absent from the underlying physics. The one piece of evidence everyone agrees on, that time is experienced, turns out to be perfectly consistent with both sides of the argument, which is part of why the argument never ends. After more than 100 years of this argument, it is worth asking an uncomfortable question. Is this actually getting resolved, or are physicists just talking past each other? The honest answer is that the disagreement is not shrinking. It may be growing. New frameworks keep appearing. Loop quantum gravity, shape dynamics, the Page-Wootters Mechanism, emergent spacetime from entanglement, and each one deepens the argument rather than closing it. More physicists are engaged with the question of time's fundamental nature than at any previous point in history, and they disagree more sharply than ever about what the answer is. There are three separate reasons the debate refuses to settle. The first is experimental. The block universe and presentism make identical predictions for every measurement physics can currently perform. You cannot build an apparatus that distinguishes between a universe where all moments coexist equally and a universe where only the present is real. Both pictures produce the same numbers. Similarly, loop quantum gravity, which treats time as emergent and ultimately absent from the foundations, and any theory that preserves time as a genuine fundamental element, both reproduce general relativity at the scales any existing telescope or collider can probe. The disagreement lives at energies of around 1019 GeV, the Planck scale, where quantum gravitational effects become significant. The most powerful particle accelerator ever built reaches energies roughly 15 orders of magnitude below that threshold. The gap is not a technical problem waiting on better engineering, it is staggering. The second reason is that serious physicists are looking at the same evidence and weighting it differently. Rovelli and Barbour look at the Wheeler-DeWitt Equation, the equation that should describe the quantum state of the entire universe, and they see time vanishing from the mathematics. For them, this is decisive. The fundamental equation has no time parameter. Therefore, time is not fundamental. The logic is clean. Smolin looks at the same situation and sees a different lesson entirely. Every experiment ever conducted in physics was performed by a specific observer at a specific moment. No measurement has ever been made outside of time. The doing of physics is irreducibly temporal. You cannot subtract the present moment from the act of observation without destroying the observation. Both of these arguments are serious. Neither one is obviously wrong. They represent a genuine difference in which facts are being treated as primary. The third reason is that the question bleeds into philosophy in ways that resist purely empirical resolution. What would it even mean to confirm that time is real? If you run an experiment and find a result, you found it now. The finding is itself a temporal event. You cannot use temporal evidence to prove that time is fundamental without some circularity. And if you try to prove time is not fundamental, you face a different version of the same trap. The proof happens in time, and the people evaluating it are using their experience of temporal sequence to follow the argument. The question is not like asking whether the Higgs boson exists. It cuts below the level at which experiments give clean verdicts. What would actually move the needle? That the experimental frontier, gravitational wave observatories are beginning to probe the strong field regime around black hole mergers in ways that may eventually test quantum corrections to general relativity. Hawking radiation, the slow thermal emission predicted to bleed from black holes has never been directly observed, but future detectors may change that. Hawking radiation carries quantum information in a way that connects directly to questions about whether information is preserved across the event horizon, which connects to whether time evolution is truly unitary, which connects to the deepest questions about the nature of time. These are not distant abstractions, they are concrete physics that observational programs are currently chasing. On the laboratory side, experiments testing the Page-Wootters Mechanism, the proposal that time emerges from quantum entanglement between subsystems, have already been performed in small quantum optical systems. The results are consistent with the mechanism. Scaling these experiments up, using larger and more complex quantum systems, could sharpen the evidence considerably. If time demonstrably emerges from entanglement in a controlled laboratory setting, that is not proof that time is absent from the fundamentals of the universe, but it is strong circumstantial evidence that emergence is at least possible. Cosmological observations of the very early universe offer another angle. The cosmic microwave background encodes information about conditions when the universe was less than 400,000 years old. Future surveys will sharpen that picture dramatically. If quantum gravitational effects left imprints on the early universe, signatures in the spectrum of primordial fluctuations, then observations of the large-scale structure of the cosmos might eventually constrain the theoretical landscape enough to rule out whole families of proposals about the nature of time. None of this will hand down a verdict quickly, but it narrows the territory. What physicists are increasingly clear about is that the resolution, when it comes, will require a complete theory of quantum gravity, not an approximation, not a limit, not a regime where one theory borrows tools from the other, a full theory. And building that theory has been the central unsolved problem in fundamental physics for roughly a century. Every serious proposal, string theory, loop quantum gravity, causal set theory, causal dynamical triangulations, has partial successes and unresolved failures. None has made a prediction unique to quantum gravity that was then confirmed by experiment. The theories are not yet complete enough to be tested in the ways that would matter most. Some physicists argue the question itself may be poorly posed. Asking whether time is real might be like asking whether temperature is real. Temperature is not a fundamental property of the universe. It is a statistical description of the collective motion of enormous numbers of particles. But it is entirely real. It blisters your hand. It governs chemical reactions. It shapes weather systems. If time is like temperature, emergent but causally potent, absent from the microscopic laws but deeply present at every scale where human beings actually live, then the question of its fundamental reality is less interesting than the question of how it arises and what it is made of. That reframing may be the most intellectually honest place to land. Not whether time exists, but what kind of thing it is and where it comes from. The question of whether time is real, and the question of how to build a complete theory of quantum gravity, are not two separate questions. They are the same question written in different languages, and neither one has been answered.